So let's jump in with where I left off. The word was amplitude. And we were talking about how that affects the wave height. And so if you think about it, it's not a constant wave height anymore. It's a variable wave height. So as x gets bigger, the wave height increases and similarly decreases. So if you want to think about this graphically, which is always kind of nice, think about the line y equals x and the line y equals negative x as being kind of the boundary lines for the amplitude of this function. And then you can start graphing it. At 0, it's going to be 0, and then it's going to start alternating like this. Okay, and so the amplitude is going to continue to get bigger and bigger. And similarly over here, it's going to do kind of much of the same thing. So it looks like the limit as x goes to 0 is going to be 0. And that's correct. You could do that by direct substitution. But what would the limit be as x goes to negative infinity, do you think, as we go out to the left? Absolute value. Well, is there going to be a limit? Over here, remember when sine oscillated between two fixed values? We said there was no limit. This one's not oscillating between two fixed values. It's oscillating between two values that are getting bigger and bigger and bigger. Yeah. So this one is also DNE. And believe it or not, it's also by oscillation, but not between two fixed values. Now, this one is kind of cool if you think about it, and it's always fun to think about infinity. As this continues to go out further and further to the left, this is going to go down towards negative infinity before it turns around again, ultimately, to go up towards positive infinity, before it turns around to go back down towards negative infinity. And if you go out far enough, are you ever going to be able to hang around to even see it turn around again? No, it's going to appear like it's going down to negative infinity forever and ever, and or up towards positive infinity forever and ever. But guaranteed that that's not the case, right? That is not the case. It's going to continue to oscillate, but between two larger and larger values. So kind of weird when you think about eternity, right? Yeah. Okay, so here's kind of the same idea, but now notice what we're doing is we're kind of making the amplitude the reciprocal of x. So as x gets bigger, what's happening to the amplitude? Getting smaller, it's decreasing. So again, you can kind of sketch this one like we did with 1 over, or the line y equals x. You could graph the line 1 over x like this, and then graph negative 1 over x, which would reflect it across the x-axis. So if you draw these guidelines in here, that can now become the boundary line for your amplitude. So now if you sketch it, it'll start here at 0, and notice right away it's going to kind of go up to infinity, but eventually it's going to do this, and it's going to oscillate, but by less and less and less and less. And if you go further out, you're not going to be able to see it oscillate, but if you were to zoom in right here, it would essentially look like that, and you could do that forever and ever and ever. So what do you think the right end behavior of this one is? 0, yeah. This one does continue to oscillate forever and ever and ever, like the previous two, but by less and less and less and less, okay? And so we do know that although it's never going to stop oscillating, it's going to approach 0, meaning it's going to deviate less and less far from the x-axis as it continues to oscillate. So this one actually has a finite end behavior limit, and it would be the same value on the other side. Now this one you can kind of figure that out by direct substitution, right? If you plug in, you get 1 over infinity, which approaches 0, but then you get 0 times dne, which doesn't really make sense. But if you just write it as sine of x over x, it kind of just changes the way you analyze things. Because now you could say, although that limit is undefined, you could treat it essentially as a constant, right? Because it's hanging out between 1 and negative 1. So if you have essentially something that's a constant, and I'll put quotations around that because it's not really, right, or a contant. There we go, put an S in there. It's between negative 1 and 1, so it's a constant interval, I guess. Over something that grows really, really big, really fast, it's going to approach 0, right? So that's kind of a way to look at it analytically. And it doesn't really matter how you analyze these, whether you think about it graphically, but analytically is going to be kind of the way we're tending towards, because a lot of times we're not going to know what the graph is. So again, with infinity or negative infinity, we're looking at end behavior. You can look at the part that contributes to the most. Okay, so this last one here was the only one that was kind of interesting after lunch because it tapered off towards 0. And so now we have our definition, okay? If, it's an if and only if, okay, so I'll start with the first part. If one of these two things or both happens, the limit as x goes to infinity is L, or the limit as x goes to negative infinity equals L. And I could say L sub 1 and L sub 2. That's probably a little bit better. Where L sub 1 and L sub 2 could equal each other, but not necessarily, okay? There's two ends of a graph, so you can have two completely different end behaviors. They could approach the same thing or something different. Then, by definition, we say f of x has a horizontal asymptote at y equals L sub 1 or y equals L sub 2, okay? So however many end behavior values you have that are finite, you'll have that many horizontal asymptotes. And so like a vertical asymptote was of the form x equals, because that's a vertical line, a horizontal asymptote is of the form y equals. So the maximum number of horizontal asymptotes any graph can have is how many? The maximum number. 2, right? How many ends of the graph are there? 2. You got the left end towards negative infinity and the right end towards positive infinity. But you can have certain functions that only have one horizontal asymptote, and they only affect the graph on one side, like e to the x, or you have something like 1 over x that we saw, I think we saw that the other day. 1 over x, the graph, has a single horizontal asymptote, but it affects the graph the same way on both sides. It pulls it towards 0 on both sides, one from the positive side, one from the negative side. And then, of course, you can have functions without horizontal asymptotes at all. Okay? So, again, horizontal asymptotes, as I said before lunch, are not, repeat, not discontinuities, even though they are asymptotes. A graph can cross its horizontal asymptotes any number of times. Here's a good example of one that crosses how many times? Infinitely many times. So I think that's a pretty good example. So the horizontal asymptote just tells us what the y values are approaching, okay? Doesn't ever make the claim that it has to get there. It certainly can, but it only approaches that value. All right, so here's example 2. Find the equations now. Let's have the form y equals for any horizontal asymptotes for this function f of x equals arctangent of x squared by analyzing the end behaviors of the graph. Use proper notation. All right. So I don't know what arctangent quantity squared looks like, the graph, do y'all? I don't either. But here's the analysis for finding horizontal asymptotes by way of the definition. If I take the limit as x goes to infinity of this function, and I'll go ahead and write it, arctangent of x squared. That would be the right end behavior. And then I'm going to go ahead, I'm going to work vertically here, so I'm going to set up this other one on my next column. The limit as x goes to negative infinity of arctangent of x squared. Okay, so this would be the analysis that you would show when you're analyzing end behavior / looking for the existence of any possible horizontal asymptotes. Okay, so now how would we evaluate that? Well, go back to what we did yesterday. We can use the property of limits that enables us to take that limit inside the power, right? So I can rewrite that as the following. The limit as x goes to infinity of arctangent of x, and then I can find that and square the result. So how is that any more helpful? Direct substitution gives you arctangent of infinity, which again, that doesn't make sense. We can't really plug in infinity per se. So we have to think about what the graph of arctangent looks like. So let's review one of the most important parent functions in BC calculus, especially the graph of arctangent of x. Arctangent of x, also known as what? Not cotangent, that's the reciprocal of tangent, inverse tangent, right? So remember, for arc or inverse tangent, the input here, the x, represents a ratio, and then the y value, the function value, gives you an angle, and it's going to be, in this case, it's going to be between negative pi halves and pi halves. That's the principal value range from pre-cal. But if we remember the graph, it's a lot easier to remember, because remember, tangent has vertical asymptotes at negative pi halves and 3 pi halves. So arctangent then, when you take the inverse, you reflect it across the line y equals x. It has horizontal asymptotes at y equals pi halves and down here at y equals negative pi halves. And then it's an odd function. It has origin symmetry, and it's a monotonic increasing function. So you take basically that one branch of tangent between negative pi halves and pi halves, you reflect it across the line y equals x, and you get the function arctangent of x, okay? So if you remember last year on the calculator, if you ever did like inverse tangent of some ratio, which could be really any ratio, you'll always either get a positive acute answer or a negative acute answer. This is the only inverse trig function that you have to know the graph of, okay? Because it's the only one with end behavior. The domain of this function is all real numbers. The range is negative pi halves to pi halves. So why is that important? Well, if I can use the property of limits to write it like the purple above, what would the limit as x goes to infinity then of arctangent be? Pi halves. Yeah, very good. That's the horizontal asymptote. So that becomes pi halves. And now we just square the result, and we end up with pi squared fourths would be the answer. Okay, so I don't know what the graph of arctangent of x quantity squared looks like, but I know that it has a horizontal asymptote where? So based upon this result, there's a horizontal asymptote at y equals pi squared fourths. Okay, and I know it at least affects the graph on the right-hand side, because that was the right-hand behavior. Well, now we'll just do the same analysis over here. Let me scoot that over. So let's go ahead and rewrite it. Might as well review the properties. Bring the limit on the inside. The limit as x goes to negative infinity of arctangent of x. And now we go to the graph where we visualize it in our head. And what do we get when we go out to the left? Negative pi halves, okay? So that's negative pi halves. But again, what are we doing with that output? We are squaring it. So when we simplify it, it comes out to be the exact same number as the positive one, pi squared fourths. So how many horizontal asymptotes does arctangent squared have? If we got the same value on both the right and the left, there's only one horizontal asymptote. Yeah. So basically, if you take this graph and you square all the y values, you're not going to have any negative values. It's going to look something like this. Here's what the graph looks like. Draw your horizontal asymptote. That's pi squared fourths. And the graph's going to look something like this. It's going to look kind of like an upside-down bell curve. All the negative values are going to be squared, so they're the same magnitude because it's an odd function. So when you square them, it's going to turn into an even function, and you only have one horizontal asymptote. Okay, so that's how we can analytically use the properties and then some known features, some parent functions to answer bigger and better questions. All right? Horizontal asymptotes. So anytime an end behavior is a finite y value, you're going to have a horizontal asymptote at y equals that y value. Okay, so that's one way to do it. Example 3 is pretty important, and this is kind of a pre-cal thing, maybe even algebra 2 thing. But in the context of a limit, maybe you haven't seen it before. There's 3 different cases for these type of functions. These are called rational functions, and we've seen them already this year. A rational function is a ratio of 2 polynomials, okay? A ratio of 2 polynomials. And we know that they can have domain restrictions. They can give you holes. They can give you vertical asymptotes depending on whether you get 0 over 0 or non-0 over 0. So that gives you all the local behavior. But we want to analyze the end behavior of the following functions. And it says to use correct notation. So to do that, let's go ahead and write it out. We'll say the limit as x goes to infinity. And I'll put the function's name there. And let's do the limit as x goes to negative infinity of the function's name. So just like we did previously with the polynomial, all we have to do is spot the pieces that are contributing to the majority of the growth for huge positive and negative magnitudes of x, all right? But because this is a ratio, and again, I emphasize that word, you can actually do some kind of analysis for end behaviors of ratios. That is, compare how fast the numerator grows to the denominator, right? So let's go ahead and do that here. In the top, because it's an end behavior or an infinite limit at infinity, sorry, just ignore everything but the leading term. And remember, the leading term is not always the one in front, is it? I can get kind of sneaky and bury a larger degree term in the rest of the stuff. But in this case, it is the leading terms. All right, so the 3 and the 5 are kind of inconsequential. The things that contribute the most to the growth are the powers there, right? So which one grows faster, top or bottom, for huge values of x? The bottom. Any cubic is going to grow faster than a quadratic. So even though they're both growing, right, here's an example. They're both growing, like if you have fractions with numerators and denominators, let the numerator grow like 1, 2, 3, 4, 5, right? The numerator is getting bigger. but exaggerate it. The denominator is getting bigger faster. So like 10, 100, 1,000. You get the idea. 10,000, so on and so forth. 1 million. What's happening to those ratios? They're getting smaller and smaller and smaller, approaching what? 0. Yeah. So remember, anytime the denominator grows faster than the numerator, by any amount, the ratios are going to get smaller and smaller, and they're going to approach 0. Okay, so that could be an x squared over an x cubed. It could be an x squared over an x to the 4th, x squared over x to the 100th. The larger the degree difference, the faster it goes to 0. But remember, these will actually never reach 0. They're just approaching it, okay? And that's from the right-hand side. If you want to know if it's approaching 0 from above or below, because 0 is the x-axis, you can actually determine that by plugging in a positive infinity. 3 positive squared over 5 positive squared is a positive number, right? So we can actually add to this. 0 is a really nice number because everything below it is negative and everything above is positive. So as we go to the right, we're going to all have positive ratios, so we know it's approaching 0 from above. That's kind of nice. So if you were just thinking about that graph, it's going to look something like this. It's approaching 0 from above. So you get more than just the information of approaching 0. Now similarly here, if I plugged in a negative, it's going to still get, the magnitudes are still getting smaller and smaller, approaching 0. But if I plug in a negative number to those leading terms, 3 negative squared is positive, right? Over 5 negative cubed is negative. And so I'm going to have negative ratios as I go out to the left. So this is going to be approaching 0 as I go to the left from the negative side, which is from below. Again, if you want to think what that looks like, it's going to look something like this. And there's a horizontal asymptote. All right, so let's go ahead and say that. Since the two end behaviors both exist, in this case they're both the same, we could say so f has a horizontal asymptote at y equals 0. And like the function 1 over x, it's affected the same way on both sides. In fact, speaking of the function 1 over x, here's another way you can get the end behavior model. Right? If you look at it locally, you'll see all kinds of cool stuff. To get the end behavior model of a ratio, all you do is just look at the quotient of the leading terms. So if you were to come off to the side and simplify 3x squared over 5x cubed, you would simplify it down to 3/5 times 1 over x, or something like that, right? So that would be a parent function of 1 over x, and the 3/5 would just be a vertical compression by a factor of 5/3. So whatever this function looks like locally, I don't know. But I know that as I zoom out into outer space, because the end behavior model is 1 over x, it's going to start looking more and more like that, okay? I'm not going to see any detail. And so the end behavior model and the function itself have the exact same end behaviors. Okay, so that's another way you could do it. But just to generalize then, any time the denominator grows faster than the numerator, the limits on both sides are always going to be 0. Always, always, always. Okay? That's case 1. Case 2. Look at this one. We're finding the end behaviors again. So if you want to write it out, it's the limit as x goes to infinity now of g, and the limit as x goes to negative infinity of g. And let's find the leading terms. Because it's an infinite limit, we'll just get rid of anything that's not the largest exponent. Okay. So there we go. If you plugged in, this x to the 5th and this x to the 5th are exactly the same, right? So if you plug in huger and huger values, it's going to be the same huge value in the top and the bottom, right? Which means they're going to effectively do what? They'll perfectly divide out. It's the same exact infinity on both sides dividing out, and what are you left with? 3/5, right? So this was always case 2. When the degrees are the same, the limits on both sides are going to be a quotient of the leading coefficient over the leading coefficient. Okay, it's always leading coefficient over leading coefficient when the degrees are the same, or when they're growing at the same rate in general. Now, we're not going to determine if it's approaching 3/5 from above or below 3/5 because that's not as easy. We can't just look at signs. We have to look at magnitude, so we're not going to do that. But because either one of those is a finite number, we could say so g, or g of x, either one, has a horizontal asymptote at y equals 3/5. And we know it affects the graph on both sides. So that's case 2. Anytime your functions grow at the same rate, it's going to be a quotient of the leading coefficients. Anytime the denominator grows faster, it's always 0. So this number can vary depending on the coefficients themselves. This number is always 0. Got it? So if that's case 2, what do you think the third case is? I think there's only one possibility. Bottom grows faster, grow at the same rate. Next one would be top grows faster. Yeah, so that's h of x. Let's set it up here. The limit as x goes to infinity of h, and the limit as x goes to negative infinity of h. So again, find that leading term. In the top, it's the first one, and also in the bottom, it's the first one. Okay, so now they're both getting bigger, magnitude-wise, but now the top is getting bigger faster. So if you wanted to do that little comparison again, let the denominator get bigger now, 1, 2, 3, 4, 5, but let's let the top get bigger faster, 10, 100, 1,000, so on and so forth. What's happening to those ratios? They're getting bigger and bigger and bigger. Okay, so they're going to be approaching plus or minus infinity, depending on the sign. Depending on the sign. Okay, so if the top grows faster than the bottom, the one-sided limits, right? Remember, infinite limits or one-sided limits are going to be either positive or negative infinity as a preferred answer. And we just need to come back and determine, is it plus or is it minus? Okay, D and E again would be a safe answer for a free response. Don't ever forget that for infinity. But how do we determine that if it's positive or negative? Yeah, plug in a positive or negative. That's one way. So that's probably the easiest way. Just into your leading terms. Plug in a positive number if we're going out to positive infinity. Into your leading terms, you get 4 positive cubed over negative positive squared, which is what? That's negative because you have a positive over negative. So it's going to negative infinity as you go out to the right. And if you go out to the left, plug in a negative infinity. 4 negative cubed is negative. Negative 2 negative squared is still negative, right? Because when you square the negative first, it becomes positive. And that positive times the negative 2 makes it negative. So when you go out to the left, it's negative over negative, which is actually positive, okay? So these have opposite end behaviors. Does this function have a horizontal asymptote based on the definition? Are either one of those finite? No, they are by definition infinite. So this has no HA. So h of x has no horizontal asymptotes, but it might have another type of asymptote. Okay, a horizontal asymptote is nothing more than a horizontal line asymptote. We can have all kinds of end behavior asymptotes. They don't have to be horizontal lines. They can be slanted lines. You can even have quadratic parabolic asymptotes. Let's look at the end behavior model here. End behavior model. If you just simplify the leading terms that I circled, you get 4 divided by negative 2. You get negative 2. And what's x cubed divided by x squared? Sorry. It's x. Okay, so this is your end behavior model. It's linear. Now, it could have some kind of y-intercept, which we don't know yet, but that just means that if you zoom out into outer space, you're not going to see all the wonderful vertical asymptotes and local max or mins. All you're going to see is a line that looks like a slope of negative 2, right, from space. Now, depending on the y-intercept, that line could be, you know, up or down. We don't really know. But as you zoom out, that's all you're going to see. That's the end behavior model. And we call it the end behavior model because it has the same end behavior as the function. So because the end behavior model, as you go out to the right, goes to negative infinity, so does the actual function. And it has the opposite end behavior if you go out to the left, which is what we have here. So you have a couple of ways to determine that. If the top is bigger than the bottom, it's always some type of infinity. You can get the sign by plugging into your leading terms, or you can predict the end behavior model. Now here's something that's cool. What if I throw in another function here? Let's call it c of x for cool of x. How about if it was something like, how about 10x cubed plus who cares? Well, no, that's not the x cubed. Let's do x to the, let's do 6, yeah, plus who cares, all over 5x to the 4th plus who cares. Would this function have a horizontal asymptote? No, remember the two cases where we have a horizontal asymptote is if the bottom is a larger degree or grows faster, it's always at y equals 0, and that's both end behaviors. If it's the same growth rate, same degree, it's always quotient of the leading coefficients. But if the top grows faster by any amount, it's always some type of infinity and no horizontal asymptote. So this one would have no horizontal asymptotes. But what does the end behavior model look like? End behavior model. Yeah, it would be 2x squared. And what is the graph of 2? And it would have some like other parts, bx plus c. But what does the graph of 2x squared look like? It's a parabola that opens up. So as you zoom out into outer space, you're going to only start to see a parabola that looks like y equals 2x squared plus something. Okay? So in fact, if you wanted to sketch this with the local behavior, you could actually sketch a dotted line. And you could call that a parabolic asymptote or a quadratic asymptote. And it would be at y equals 2x squared. So here's what it would look like. If we get all the local behavior in there, which I'm not going to find, you might have some of this stuff. There might be like a local max there. And what might happen is it might live up in here, and then it's going to do this. It's going to go to infinity along the path of that parabola. And then over here, it might live in this little section, and it might go up to infinity. So that would be all the local behavior. But I guarantee that if you were to zoom out, this is all that you're going to end up seeing. So the end behavior model itself ends up becoming part of the equation of your end behavior asymptote. Okay? I didn't do that over here, but what would happen if you simplified your leading terms on this guy? Your x to the fifths would divide out, and so the end behavior model is the horizontal line, y equals 3/5. So not only is it a horizontal asymptote, right, for the local behavior, but when you zoom out, that's all you're going to see. You're just going to see that horizontal line, y equals 3/5. Okay, so pretty cool. So you can have end behavior asymptotes of any degree. You can have cubic, quintic, quartic. It's whatever the degree difference is. Now, what are the ones that you're responsible for? Of course, the horizontal asymptotes at 0, the horizontal asymptotes at whatever the number, and later on, we're going to find those. Those are going to be called slant asymptotes. All right, so cool. We got through example 3. Have a fantastic rest of the day.